In this video, I will show you some applications of parametric equations. If you don't know what parametric equations are, you should probably go back and watch my introductory videos first. You can either click the link that appears in the upper right-hand corner or find the link in the description. Let's start off with some notes. For an object launched at an angle theta with the horizontal at an initial velocity v0, where g is the gravitational constant, and t is time, and h0 is the initial height, the horizontal distance is t v0 cosine theta. This is just the horizontal component of the initial velocity times the time. The vertical distance traveled will be t v0 sine theta minus 1/2 gt squared. This first term is the vertical distance the object would travel if there was no gravity. It's just the vertical component of the initial velocity times the time. The second term is the distance the object would fall during time t if the object were simply dropped near the Earth. If we wanted to change this to a formula for vertical position instead of the vertical distance traveled, we would need to add the initial height of the object. The g mentioned in the vertical distance formula is the acceleration due to gravity. Near the Earth, g equals 9.8 meters per second squared, which is about 32 feet per second squared. Example 1. Hayden kicks a soccer ball with an initial velocity of 43 feet per second at an angle of 34 degrees. Part A. Write a set of parametric equations to model the movement of the soccer ball. The horizontal position of the ball x of t will be given by t times the initial velocity times cosine theta. So that's t times 43 times cosine 34. Instead of writing t times 43 times cosine 34, I will simply write 43t cosine 34. Similarly, the vertical position of the ball would be 43t sine 34 if there was no gravity. Near the Earth, we must subtract the 1/2 gt squared, and since we're dealing with feet, let's consider g 32 feet per second squared. So this is really 1/2 32t squared, which is 16t squared. Just for fun, let's put these parametric equations into the graphing calculator and see what we get. Hit the mode button on your calculator and go down to where it says function versus parametric and make sure that parametric is selected. Then under y equals, you can go ahead and type in the parametric equations that we found. Let's adjust the window a little bit. Let's let t min be 0 because we're starting with time 0, and t max 10 is usually a good number. T-step controls sort of the speed of the animation in this case, and the smoothness of the graph. Let's use 0.01. Let x max be 75 and let x min be 0, and let's go ahead and let y min be 0 and y max be 10. By the way, one more thing back on y equals, I recommend changing this setting right here. So arrow over to this and hit enter. And then if you use your, not the color, if you go down to the line and you switch this around, it toggles between these different options, and I would like you to choose this one because it allows you to see the animation in motion. And then hit OK. So let's hit graph and see what we get. So you can just imagine the soccer ball being kicked up into the air and coming back down. Part B asks, how high is the soccer ball after 1.2 seconds? For this, we will need our vertical position formula. Notice that I left off the initial height when I wrote down the formula. That's because we are assuming that the soccer ball is on the ground. So the initial height is 0, which we did not need to write. So we need to evaluate y at 1.2. So let's plug in 1.2 for t here and here. That gives you this expression. Since we've already typed this into the calculator, we could use this to evaluate y at t. But we need to change one setting first. Hit second window for the table setup menu. I'd like you to come down to where it says independent and auto, switch it to ask. If you do this, now you can hit second graph for the table menu, and it's just waiting for you to type in a value for t, and it will automatically evaluate x at t and y at t. So we wanted to see what happens when t is 1.2, so type that in and hit enter. So this is the horizontal position at 1.2 seconds, and this is the vertical position that we were asked to find. So 5.814. Let's always use 3 decimal places, and please do not forget your units. Very important. Alternatively, you could go to a blank screen on your calculator and type in this whole expression and hit enter. You're going to get the exact same answer. Part C. When does the soccer ball hit the ground? The question when means we need to find t. The fact that the ball is hitting the ground means that the vertical position y of t equals 0. So we are setting y of t equal to 0, and we're solving for t. We can factor out the common factor of t. Using the zero product property, we can solve by setting each of these two factors equal to 0. Setting t equal to 0, we get the fact that the soccer ball was on the ground at time t equals 0. That's not what we're looking for. So let's go ahead and set the other factor equal to 0 and solve. Let's add 16t to both sides of the equation. So that will give us 43 sine 34 equals 16t. Dividing both sides by 16, we get this expression. Let's put this in the calculator. So that is 1.503 if you round up. So the ball will hit the ground after 1.503 seconds. Part D. How far does the soccer ball travel before hitting the ground? The question how far tells us that we need to evaluate the horizontal position function x of t. The fact that the ball is hitting the ground tells us that we need to use the time when the ball hits the ground. That's what we just found in part C. The ball hits the ground at 1.503 seconds. So we need to evaluate x of t when t is 1.503. To make sure we don't lose any decimal place accuracy, I would like to store this whole number into a letter. So let's go back up to it and hit enter. And then let's hit the store button and choose the letter T. We have now stored all of these decimals into the letter T. Back in part A, we wrote the formula for x of t, 43t cosine 34. Now we need to find x at 1.503, so that'll be 43 times 1.503 cosine 34. But in my calculator, I'm just going to put in a t right here. So I'm typing in 43t. Don't use this button. Use your alpha t cosine 34. So that's 53.574 if you round up. So the soccer ball will travel 53.574 feet before hitting the ground. Part E. When does the soccer ball reach its maximum height? The fact that we are looking for a height means we need to evaluate the height function y of t, which happens to be a parabola. Because we are looking for the maximum height, we need to find the vertex of this parabola. The x-coordinate of the vertex will be the time at which the ball reaches the maximum height, and the y-coordinate will be that maximum height. Back in Algebra 2, we learned that given a parabola in standard form, the x-coordinate of the vertex would equal opposite of b over 2a. Here's the vertical position or height function we found back in Part A. Here's that same formula rewritten in standard form so that you can see that A is negative 16 and B is 43 sine 34. So if the vertex occurs at opposite of B over 2A, then in this case the vertex will occur when t equals negative 43 sine 34 over 2 times negative 16. Negative 43 sine 34 over 2 times negative 16. Kabam! 0.751. So the ball reaches its maximum height at 0.751 seconds. Part F. What is the maximum height of the soccer ball? Because we want the maximum, we are again talking about the vertex of the height parabola. But because we want the actual height and not the time, we want the y value. We already found the x-coordinate of the vertex, or I should say the t-coordinate of the vertex. We just need to plug this back in to the height formula to find the height at that time. So we just need to type this into our calculator. However, to avoid a rounding error, I'm not going to use the rounded number 0.751. Instead, I want to store this entire number into a letter on the calculator. So go up, hit enter, and hit store, and you can use any letter. I'm just going to use T, so alpha T. So now I can type in this formula using a T instead of 0.751. Just like this. So we get 9.034. So the maximum height of the soccer ball is 9.034 feet. Example 2. You throw a rock off a cliff 900 feet high with an initial speed of 90 feet per second at an angle of 45 degrees above the horizontal. So V0 is 90 feet per second, H0 is 900 feet, and theta is 45 degrees. Part A. How long is the rock in the air? How long means we need to find time. How long is the rock in the air is another way of asking how long before the rock hits the ground. So we need to find when the vertical position is equal to 0. Remember, here's the formula for the vertical height of an object, given initial speed, initial height, and the initial angle. Plugging in our initial conditions and setting the vertical position equal to 0 gives us this. For this problem, I'm going to use 32.174 feet per second squared as the value of g. Given a quadratic equation in this form, the quadratic formula tells us that the solution is this. So I'm just going to reverse these terms to put it in standard form. In this form, it's easier to see that this is A, this is B, and this is C. In other words, A is negative 1/2 times 32.174, B is 90 sine 45, and C is 900. I am going to define A, B, and C on the graphing calculator as each of these quantities. For example, I type this in, and then I hit store, and alpha A. Kabam! Similarly, I have stored this value into B and this value into C. So according to the quadratic formula, we can find a solution to our quadratic equation by typing in the opposite of B. We can't do plus or minus, so I'm just going to do plus for now. The square root of B squared minus 4AC all over 2A. So here's one solution, but this is a negative value, which is invalid in the context of this problem. We are looking for time t, but time can't be negative. So let's do the quadratic formula again, but this time with a minus. We don't need to type in the whole thing again manually. If we go up and highlight and hit enter, we can now edit our previous expression. So I'm just going to go back to the plus, and in the quadratic formula we have plus or minus. We already did the plus, so now we will do the minus. 9.715 if you round up. So the rock will be in the air for 9.715 seconds. Part B, when is the rock at its maximum height, and what is it? The maximum height of the rock will occur at the vertex of the parabola, and this will happen when t is opposite of b over 2a. So let's type it in. Opposite of b over 2a. There it is. Let's store this value into letter t so we can use it to answer the next part of the question. If we just immediately hit store, it uses the value that we just found, and let's put it in letter t. So t is 1.978 seconds if you round up. We know the height of the rock at any time t is given by this expression. We just need to evaluate at 1.978. So here it is all typed in, and we get 962.939 feet. So that's it for part B. Part C asks, how far horizontally does the ball travel? Small correction, for this problem we are talking about a rock and not a ball. Anyway, we need to find the horizontal position of the rock, which is given by this formula. Specifically, we need to find the position when the rock hits the ground, which is at 9.715 seconds. So we can just type this into the calculator, and we get 618.259 if you round up. So the rock will travel 618.259 feet before it hits the ground. Let's do one more. Example 3. Kyle is practicing free throws for an upcoming basketball game. He releases the ball with an initial velocity of 24 feet per second at an angle of 53 degrees with the horizontal. The horizontal distance from the free throw line to the front rim is 13 feet. The vertical distance from the floor to the rim is 10 feet. He releases the shot 4.75 feet from the ground. Does Kyle make the basket? In other words, is there a t at which x of t, the horizontal position, equals 13, and y of t, the vertical position, is equal to 10? Our strategy will be, first find the time t when the horizontal position x of t is equal to 13. Then, see if the vertical position y of t is equal to 10 at that time. We are given the initial velocity 24 feet per second, the initial height 4.75 feet, and theta is 53 degrees. We will use 32.174 feet per second squared as the acceleration due to gravity. Our first step is to find the time t when the horizontal position is equal to 13. Here's the model that gives the horizontal position of the ball. So we need to find when 24t cosine 53 is equal to 13. Let's divide both sides of the equation by 24 and cosine 53. The horizontal position will equal 13 when t equals 13 divided by cosine 53. If we type this into the calculator, we get 0.900 seconds. Let's store this into letter t. Alright, now it's in there for later. Our next step is to find the vertical distance at 0.900 seconds. If it turns out to be 10 feet, Kyle makes the shot. This is the formula for the vertical position at time t. Using our initial conditions and t equals 0.900, we get this. Let's just put it in the calculator. So when the ball reaches the hoop, it has a vertical position of 8.970. That's a little short of the necessary height of 10 feet, so Kyle misses the basket. In summary, we can say Kyle misses the basket because the vertical position of the ball is less than 10 feet when it reaches the hoop. We've all been there, Kyle.